someone in the audience test and make sure we can hear? I am. Okay, can we hear? No. No?
Wait.
There it goes.
Yes, we can. It's delayed by like 20 seconds.
Okay. So, as your lab instructors have told you, there is a midterm next week. It'll be during your class time and it's all multiple choice. Some instructors are having you come in, others are doing other things, but if you're in my class, I'm Miles, obviously. If you're in my class, my Tuesday, Wednesday class, be sure to be on time. And if you want to be early, you can ask me any last minute questions you have, and you can always email me. So let's start off with Lab 1, Math Essentials. Starting in your lab manual, we are on page 1. So remember, there are 2 types of maps. We talked about these if you went to travel somewhere, if you were at a roller coaster park, you have your reference map and your thematic map. Your reference map would be using to find a specific location and it's used for navigation. It's your GPS, it's your travel map, it's those maps. Then you have your thematic maps, which use to show specific data. They're colorful, they're dynamic. If you were at a theme park, they might show you where Mickey Mouse is or where the Haunted Mansion is. That's the theme here, is roller coasters. So those are our thematic and reference. So let's look at some examples of our reference maps. So obviously here we have a bit of JSU. So you could use this map from navigating from maybe your Southerners practice to where Merrill Hall is. So that is our navigational map. Here's another example of what these might look like. If you're following along, we are on page 3 now. So again, this is an example of what a reference map would look like. Here's a pretty good one of the United States, or navigational map reference one. So this is showing us United States. If you wanted to look at perhaps how far it is from Alabama to Washington, you could use that for referencing, for navigating. So here's an example of a thematic map. The theme here is the damage done to the JSU campus. So it's colorful, it's got a lot going on, and it's telling us about this area. So a lot of times you see thematic maps with political maps. In my class we talked a lot about those. So here's soil moisture. So the theme here is soil. So we see that change over time. Again, this is very colorful. So that's a good thing to look out for. Here's another example. So the theme here is percentage of 75 years of age and older in Texas. So again, it's very colorful. Its theme is age in Texas. So now let's talk about scale. Again, if you're following along in your lab manual, we're on page 4 now. So scale is defined as the ratio of actual area on the Earth's surface to map space. So if you look at, we have a scale bar on page 4. So if you took that scale bar and put it on a map, that's the map surface to Earth surface. So there are 2 types of scale you need to keep in mind. Is it zoom right here? I forgot where the camera's pointed.
If you go over this way, you can't see.
Okay.
Yeah, it's okay. I did the same thing
My
for
bad.
the other one.
Sorry guys, we're using a different camera setup than we normally do, but the important stuff's on the PowerPoint, which you guys can see. Lovely. Thank you again to Dexter for being our technology GTA. So yes, there are 2 types of scale. There's our large scale and our small scale. Our large scale shows smaller area. I like to explain this as it's zoomed in. It's got a lot of details. If you took a picture of a group of people and you zoomed in on it, it shows a smaller area. So maybe it only shows one person, but you can look at them and you can see that they have freckles or they have jewelry on. So you've zoomed in on them. It's large scale. Looking at that group of people again, if you look at a small scale picture of them, you see maybe there's 3 or 4 people next to them. Maybe they're all wearing matching Frisbee team jerseys. So you see less detail, but you all see that, oh, it's small scale. They're all wearing Frisbee jerseys. That's the detail you see there. But that's less detail. You don't see their details on the people themselves. An example of this would be the globe of the Earth. You don't see Pelham Road on the globe of the Earth, but you can see Australia. So those are our 2 types of scales. Are there any questions so far?
No.
Awesome. So if you're following along now, we're on page 5. If you want to take a moment, and if you're watching this later, you can pause the video and try and guess which one, or not guess, make an educated guess on which type is which. So here's our large scale and our small scale. So our large scale is a very zoomed in area of Jacksonville, whereas our small scale area is zoomed out and shows, I believe, more of the Calhoun area. So let's look at another example. Again, if you're watching this later, if you'd like to pause and consult your lovely lab manual, page 5. Pause now, and then let's talk about the answers. So this is Atlanta on the small scale area. You don't see much of Atlanta, but you see it's just a blob of roads, and there's some forest areas, and there's interstates and highways. Whereas the zoomed in areas, you see blocks, you see the main interstate area, and you see some building outlines. So those are large and our small scales again. Okay. Here's just another example of New York City versus the state of New York with the little island off to the side. So again, differences in scale here. I think we have another example. Oh, no. So let's talk about the anatomy of a map in Riga, Latvia. So if you think about the Alabama map that you had to label, one of the first things you would have done, hopefully, or one of the things you did later, was think of a really cool title to give it. Maybe you called it important locations to me in Alabama, or counties and important locations in Alabama. But what you want to have is a good title for your map. So it tells your readers what this map is, why is it important. Next, you're going to have your symbols. When you're making these, I think you use stars. Some people use circles. Some people do a little gamecock to represent what Jacksonville is. But these symbols, in our Riga, Latvia example, are number 3. So we have blue for water, a star for the Capitol building, and so on. So with those symbols in the legend is the legend. So the legend is just the organization of where our symbols are. Then we have the scale. We talked about this a moment ago, but this is just showing us how much map space to actual space there is. And this is a pretty large scale area. It's very zoomed in. Then we have our compass arrow, or our compass rose, whichever we're going to call it. It's just showing us the direction of north. Then we have our grid or ground rule, which again, so that's showing us that on this example, 1 square, for example, over in the water is exactly the same as 1 square inland. So it's showing us that those are the exact same area across the map, same amount of space. So let's talk about RF, representative fraction. We jumped around a little bit, but we're back on page 4. Not quite sure where the slides are at over there. But representative fraction, so 1 unit of object placed on the map is equal to X amount of those same units in actual space on the Earth's surface as shown on the map. So again, we're talking about scale here, but we're talking about what 1 unit equals. For example, you could say 1 banana in real life equals 1 banana on the map. So one banana is equal to 12,000 bananas on those maps. Some people use their phones, their shoes, as long as it was same unit on both sides of the semicolon. So yes, let's talk a little bit about that. So how do you write your RF or your ratio? So you can say RF of 1 to 17,000 can be read as 1 in 17,000 miles, or whatever unit you want to use. You want to use bananas, you can use bananas. I think miles is the best unit of measurement though. So a scale with 1 in equals to 900 bananas has representative equal fraction, or RF, again, interchangeable, as 1 to 900. So, any questions? I know representative fraction can be a little bit confusing.
Nothing yet.
That's great, you guys understand everything, I love it. So, let's pass it on. Oh wait, I'm in the first section on this, I think. No? Oh, why is it stuck on there? I don't know. Well, I'm gonna pass it off to Emily.
Okay. Hello everyone. So now we are moving on to lab 2. And remember, we're covering the key topics from each lab that's really going to show up on your midterm. So these are the important topics for the midterm. We're not covering everything, but make sure that you know what we are talking about tonight. So latitude and longitude. Latitude and longitude, that is that invisible grid that's laid over the Earth's surface. It's invisible, so it's not actually real lines that are there. The first part is latitude, so that's the first number in any coordinate that you're going to see. Latitude is always the first number in a coordinate. Latitude is also referred to as parallels, so you could call them lines of latitude or parallels. And then they are horizontal lines that measure the degrees north and south. And so the most important line of latitude is the equator, that's right in the middle at 0 degrees, and then it goes up to 90 degrees north at the North Pole, and it goes all the way down to 90 degrees south at the South Pole. So equator, not the equator, for latitude, the highest degree it can go to is 90. So 90 is our highest degree of latitude, and the equator is the most important line of latitude. The equator also separates the northern and southern hemispheres. So we talk about the hemispheres a lot in our later labs. So this is where that idea comes from. It's separated by the equator. For longitude, that is our second number in a set of coordinates. Longitude always comes second. Longitude measures east and west, where our latitude measures north and south. Longitude is east and west. And so that starts right at the prime meridian that runs through Greenwich, England. So a long time ago in the 1800s, a bunch of scientists got together and they decided the prime meridian was going to run through Greenwich, England, and they decided it, so that's what happened. So the prime meridian is 0 degrees in England, and it goes 180 degrees east, and it goes 180 degrees west, and it meets on the other side at the international date line. So all lines of longitude are the same length because they go from pole to pole. Our lines of latitude are different lengths because they go from the equator, which is the thickest part, and then they go up to a pole, which is smaller. So lines of longitude are equal lengths, and the highest degree is 180. So you can't have a degree of longitude higher than 180. Now here's our international date line. This is on the other side of the prime meridian. And so if you cross this line, let's say that we're in Alaska and it is Monday, and we cross from Alaska into Russia or Japan on the other side, is going to gain 1 calendar day, so it will be Tuesday. So if it's Monday in Alaska and you get on a plane or a boat and you pass that international date line, it will be Tuesday. So remember, it is a gain of 1 day. So the thing is though, the 180 degree line of longitude does not term in time zones. So that line itself is a straight line, but the line that you see on the board on this PowerPoint, that jagged line is the actual time zone line. But our actual line of longitude 180 is straight. Now here's some more pictures of the hemispheres. Remember, these are important because we talk a lot about them in labs 4 and 5, how they affect our seasons with the tilt and everything. So these are our hemispheres: northern, southern, eastern, and western. And they're divided by the equator and the prime meridian and international date line. Now here is our longitude and longitude grid laid over the Earth, and we are going to pick out some points and practice finding their coordinates. And so this is very basic coordinates, just degrees. We're not getting into minutes and seconds yet. So why don't we start with New York. So we see where New York is, and the first thing you got to find is latitude. Remember, latitude's always first. So our latitude, New York, looks like it's in between 30 and 45. So I would guess maybe like 40, maybe 41 degrees north is our latitude. And then for longitude, it's almost on that 75 degree west line. So maybe like 74 if I'm estimating. So our coordinate would be 41 degrees north, 74 degrees west. So that is for New York. Let's do another example. How about Hong Kong? We'll do Hong Kong over in China. So latitude is always first. It looks like it's in between 30 and 15 degrees north. So I'm gonna guess maybe like 20, I would say like 20 degrees north. And then for our longitude, it's in between 105 east and 120 east. So I would say about like 116, maybe 116 east. So our coordinates for Hong Kong are going to be about 20 degrees north and 116 degrees east. That's just guesstimating, I'm eyeballing it. So now that we know how to find coordinates on the map, now there's other ways to show coordinates. So we have been talking about degree minutes and seconds, but you can also show it as just decimal, so just decimal degrees. Can you see my mouse on the screen?
No.
No? Okay. So we know our degrees, minutes, and seconds. Degree is always shown with that little circle is a degree. Our minute symbol is kind of like an apostrophe. It just looks like an apostrophe is our minute symbol. And then our second symbol is like quotation marks, so it's like 2 apostrophes. And so you see up there at the latitude, it says 33 degrees, 49 minutes, 30.8 seconds north. That's how you read that out. And if you convert it into decimal, it's going to be 33.82522 degrees north. So what we're going to do together is work through some of these problems, just 2 examples of how to do this, because you may have to do this on the midterm. So first things first, we're going to do degrees, minutes, and seconds into decimals. So I'm going to talk through this because we don't have a marker or like a way to draw on the board, so I'm just going to talk you through it. So when we're going from degrees, minutes, and seconds into decimal degrees, the first thing that we want to start with is our seconds. So I'm going to start with that top number, 27 degrees, 42 minutes, 45.5 seconds north. We're going to start with our seconds. So I'm going to take 45.5 out, and I'm just going to work with that right now. So 45.5, and we are trying to convert that into minutes. So to convert it to minutes, we need to divide by 60 because there's 60 seconds in 1 minute, and that's our conversion factor right there. So we're going to do 45.5 divided by 60, and that gives us 0.7583. So we just converted those seconds into minutes. And so our minutes is 0.7583, and we're going to add that to our original minutes of 42. So taking that decimal that we just made, adding it to 42, that gives us 42.7583, and we need to convert that to degrees to get our final answer. So to convert that to degrees, we're going to divide by 60, because 60 is our conversion factor, because there's 60 minutes in a degree, so the magic number is 60. So if we take 42.7583, divide by 60, that's going to give us 0.7126. And all we have to do to get the final answer is add that to our original degree of 27. So remember, all we did was convert minutes into degrees, and we're adding it back to the original degree. So that gives our final answer of 27.7126 north. So that was a lot. Let's do the next one again together. Just gonna talk through it. So this bottom one is 85 degrees, 19 minutes, 29.5 seconds east. And so we're gonna always start with the seconds, which is 29.5, and we have to convert it to minutes, so we're gonna divide by 60. 29.5 divided by 60 is 0.49167. So now that we made that into minutes, so we're gonna add it to our original minutes of 19. So 19 plus the 0.49167 is 19.49167. And then we need to convert that to degrees, so we need to divide by 60 to convert it to degrees, and that gives us 0.32486. And for our final step, to get our final answer, is adding what you just converted back to the original answer of 85 degrees. So altogether, the final answer is 85 degrees, 85.32486 degrees east. Don't forget your direction. Direction is very important. It's the unit. If you don't have the unit, then you don't know what exactly that number means. So don't forget your direction, east or north or whatever it is. You gotta have that on there. So we just converted degrees, minutes, seconds into decimals. And the main thing to remember there is that you're dividing. You divide by 60. For the next one, when you go to decimal to minutes and seconds, that is when you multiply. So let's do that. Now we're going to be multiplying by 60. So we're taking a decimal and we're multiplying it by 60 so that we can get a bigger number, and that's going to be our minutes and our seconds. So the first thing that we're going to do, we always leave.
Melanie, we have a question.
Yes.
Could you actually do this on the board? It won't be very easy to see, but we have a request.
If you write B,
See, I can try.
Yeah, I would say, I know it won't be super easy to see, but,
Which one they want me to do?
you just put the next one on the board.
This one, the new one? Okay, let's see if we can see this. Right here? Okay, the marker's the problem. Oh, yeah. You see that?
1 second. Wait for the stream to catch up. I see it.
Kinda, yeah. Oh, there it goes, yeah.
Okay. Alright, so we are working on converting decimals into minutes and seconds. So here the trick is to multiply. What we did before was divide. Now we're multiplying. So always gonna leave the degree, whatever is in front of the decimal, we leave the same. We don't change it. It's gonna be the same in the final answer. So we're leaving our 34 alone, and we only wanna work with just what's behind the decimal point. So I'm gonna take this out and do 0.437287. And remember what we're doing here, we're multiplying, because we're trying to turn a decimal into a larger number. And how you do that is you multiply. Remember 60 is the magic number here, because there's 60 minutes in a degree, there's 60 seconds in 1 minute, it's the magic number. So if I multiply this out, it gives me 26.23722. And so I'm gonna take a part of this and use it for my final answer. So I'll start writing, can you see it over here?
1 second. Yes.
Okay, I'll start writing my final answer over here. So we know that 34 is gonna be in our final answer, and now we know 26 is in our final answer. So remember, always taking what's in front of the decimal into our final answer. So here we have 26, and that's minutes, because we converted it into minutes here. And now we need to find the seconds. So just working with what's left over behind the decimal now. I'm gonna multiply by 60, and that's gonna give me what I need to find our final answer. Okay, so I multiplied this decimal by 60. That gave me 14.2332. Remember, all that we need is what's in front of the decimal. We don't really need what's behind it. So we're just taking that 14, and that's seconds. Don't forget your direction is north. This is our final answer right here. 34 degrees, 26 minutes, 14 seconds north. So we just converted this decimal into this. So that was our latitude. So if we're good with this, I can go to the longitude. So we'll do it again with a different number. I feel old school.
I prefer old school.
Okay, so now we're working with our longitude. So I'm gonna write it on the board, 119, 713. Don't forget your direction. Okay. Remember, think back to what we're doing. We're trying to convert the decimal into minutes and seconds. So we leave that front number alone. It stays what it is for the final answer. So it's gonna be 119 degrees, we know that. Now we're trying to find the minutes. So we're gonna take the decimal degree here, and we're gonna multiply by 60 to convert it into minutes for our answer. So when you multiply that, that gives you this big number. So we got 42.82914. The only part we need for our final answer is this 42 in front of the decimal. So I can go ahead and add that in over here, 42 minutes. And then we gotta convert this decimal minutes into seconds. So I'm gonna write that out, 0.82914 multiplied by 60. That's gonna give us seconds. So when you multiply this by 60, you get 49.7484. And so the part that's important to us here is this 49 in front of the decimal place. And so we are going to put that in our final answer, 49 seconds, and the direction is west. So here's our final answer, 119 degrees, 42 minutes, 49 seconds, west. So we just converted this decimal into that. Do they want me to draw the other ones on the board? Since I just talked to that.
Seems to be.
Yeah, it's about small and large scale.
Any other questions?
I would, since you talked about the small and large scale, I would advise the student to go back and watch once the stream has ended. In lab one.
Do what? You're good. Okay. Alright, so that was everything with latitude and longitude. The main thing is to remember, what lines are latitude, what's longitude, what direction it runs, and how to convert them. So you definitely want to know how to do that. So now we're moving on to lab 3, the atmosphere. Miles is going to come back here and talk, and I'll come back in just a second. So moving on to lab 3.
Sorry, my bad.
So, lab 3, the atmosphere. We are on page 18 of your lab manual. So if you take a moment, go ahead and do that. Get to the right page. And we're going to talk just briefly about the gases, and we're going to throw it back to Emily so she can talk about the different layers of the atmosphere. On this slide. Okay, well, I thought that's where you put it. No, I had this. Oh well. So, what is the atmosphere? Have you gone outside before? You've experienced it. The atmosphere is the ocean of air which surrounds all of us from the Earth's surface and up into space. Gravity is holding down this ocean of air to the surface. So you can have gravity to thank for that. So let's talk about the formation of the atmosphere. We're on page 18, 19-ish. So it began about 4.6 billion years ago and mostly contained hydrogen and helium gases. Over time, water vapor and CO2 eventually replaced those gases, and early forms of life used CO2 and filled the atmosphere. They were inhaling and exhaling. Some of that got cut off, which is a bummer. But yes. So So let's talk about the permanent gases and the variable gases. There's a great chart on this on your page 19. It's kind of hard to tell where the little bitty gases are, but the main ones are the red and blue ones, which are going to be the important ones. So permanent gases, the ones that take up most of this graph, are nitrogen and oxygen. Our nitrogen is 78% of the atmosphere, and oxygen is 21%. And 0.993% argon make up the permanent gases. And there are other permanent gases that are minimal in value or volume that are in our atmosphere, but they're less than 1%. So then we have our variable gases. This is our water vapor, which is really important. We'll talk about that in just a moment. Our carbon dioxide and our ozone, O3, and other particulates, which are small parts of the atmosphere that come from liquids and solids. Some are made up of human or non-human things. But water vapor, which is really important, hopefully we'll be getting more of that lately, It's one of the most important as it influences humidity, things that makes your hair big, sources for cloud formation and precipitation. Precipitation is a big word for it's raining. So we like rain, it's what waters our crops, and we like food, so we need it. So those are our permanent and variable gases. Any questions on those? And their percentages? Cool. Oh, here's a good picture from your textbook. Again, nitrogen is well over most of the atmosphere for composition of it. It's a big blue circle. Back to Emily.
Okay, now we know what the atmosphere is made of, we know its composition, so we can talk about how it is separated by layers. So we know what's in them, now we can talk about the actual layers. And so there's 5 different layers, and they are separated by their unique temperature characteristics. So each of them has a different temperature at which the layer rests at, and it also is divided up by how much energy that layer absorbs from the sun. So that's going to affect the temperature that it is in that layer, and is a big part of why we divide them into these layers. So we're going to be filling out this graph or chart together as we talk about each of the layers. So the first one is the troposphere. This is where we live. Everything that we do is pretty much in the troposphere. This is where all of the weather happens, all of that water vapor Miles was talking about. It's all mainly located in the troposphere. The key things to remember for the troposphere is, like I said, weather happens here, but another really big thing to remember for the troposphere is as altitude increases, our temperature decreases. So if you look on this chart, you see a red diagonal line. And so it's starting at 20 degrees Celsius, and it's going all the way down to negative 55 degrees Celsius. And that's also, you see on our y-axis right here is height, or that's going to be altitude. And so as our troposphere, as we're going up in altitude in the atmosphere, the temperature is decreasing. So this is important to remember for the troposphere. As altitude increases, temperature decreases. The cause of this is because the Earth's surface is very warm, it absorbs a lot of energy, and it holds and traps heat. And so as you get away from that Earth's surface, it gets colder and colder. So this is why the temperature decreases. Going to our next layer is the stratosphere. Remember, our layers are divided by a pause. This is kind of like a temperature pause, kind of like a buffer zone for the temperature to change from one layer to the next. And so in between our troposphere and our stratosphere is the tropopause. That, like I said, is just a little buffer zone for the temperature to change and transition to the next layer, which is the stratosphere. Some key things about the stratosphere. This is where airplanes fly. That's a little fun fact. Airplanes go up above the troposphere into the stratosphere because all of that weather, the rain, the clouds, they'll be above it, and flying in air that's a lot more stable. They want to be able to be above all of the storms and weather and go into the stratosphere where it's a lot safer and more stable to fly. Another thing that's important about the stratosphere is the ozone layer. This is probably the most important thing about the stratosphere is the ozone layer. And this is what's going to cause your temperature to start increasing again. So if we know anything about ozone, I hope that you know it absorbs harmful radiation from the sun. This is something we talked about a lot. Ozone absorbs all of that harmful radiation, and it causes the temperature to go back up. Now, if you look at the line, it only goes up. It goes from negative 55 degrees Celsius up to 0 degrees Celsius. So I know that's not very warm. Like we keep talking about how it's warming up to 0 degrees Celsius. Now I know that's not warm, but in comparison to negative 55, it is warming up from all that radiation that the ozone is absorbing. That's really the main thing for the stratosphere to remember is the ozone layer and that increasing temperature because of the ozone layer. Now we will talk about ozone in just a second after we go through all the layers. Our next layer is the mesosphere. This would honestly be the layer where not a lot of stuff is happening. Remember, in between them is the stratopause, our little temperature buffer zone for the layer to change into the mesosphere, and our temperature is going to significantly decrease. It goes from it goes from 0 degrees Celsius all the way to -90. So it gets really, really cold. The cause of this is because there's not really any oxygen or any of those gases that absorb energy from the sun. So since there's none of those gases absorbing energy, there's nothing to make the temperature warmer. So it really just gets colder and colder all the way down to -90. So the coldest that the atmosphere kind of gets. Next layer, like I said, the mesosphere doesn't have a lot going on, but the next layer is the thermosphere, where there is a lot more going on, and in between them is the mesopause, our temperature buffer zone, for allowing the layers to transition and start getting that temperature to warm back up again. Some key things about the thermosphere: it has two important things inside of it. So one of the things is the ionosphere. This is a very, very small layer, not really even a layer. It's just a very small ring through the atmosphere that contains a lot of ions. If you remember what ions are, they're charged particles. And so we actually use these charged particles in the ionosphere to use long-distance radio communication. So we send up radio waves, they hit these charged particles in the ionosphere, and the radio waves come back down to Earth. So this is what we use to talk over the radio. So the ionosphere is important to us, so it's good to know that it's there in the thermosphere. Another thing in the thermosphere at this altitude is the auroras. So those are also known as the northern lights or aurora borealis. It's those northern lights that are really pretty up around Alaska and towards the poles. You see them, and this is the altitude that they're at. So if you see where the height is in kilometers, they're all the way up in the atmosphere in the thermosphere. So very, very high up there. If you notice, our temperature line is going off the chart. It's so hot. The temperature is rising all the way off the chart. The reason of this is because these are the layers that are closest to the sun. So the exosphere and the thermosphere are closest to the sun, and so they're receiving all of that sunlight and solar radiation first. They're hitting it and receiving it the hardest from the sun, so it's the hottest there, especially the exosphere. That's definitely where it's going to be the hottest. Think of the exosphere, exo is like outside, like the exoskeleton. It's kind of like our atmosphere's crust around us, and that's where it's going to be the hottest, and it is our outermost layer. So those are all of the layers, all 5 of them. And then we're going to go back and touch on ozone because it is so important and has a lot more to do with our air quality. We're going to touch on it a little bit more. So ozone is an O3 molecule, so it's 3 molecules of oxygen. And the thing about ozone is that it likes to break apart. It's very unstable. So oxygen likes to be with a pair. It likes to be O2 with a pair, with a buddy. And if it's O3 or O1, it doesn't like that because it's not paired with a buddy. So it's very unstable. It's breaking down, reforming, breaking down, reforming at a constant pace. And normally this breaking down and reforming is balanced at an equilibrium, but the problem is the equilibrium gets thrown off by CFCs or chlorofluorocarbons. So these are like pollutant, like emissions that humans release, CFCs, and they are able to break down ozone, and it doesn't reform. It breaks down, it does not reform. So this throws off our equilibrium that the ozone layer maintains. And if it can't maintain that equilibrium, then that's how you get a hole in the ozone layer. And so this is bad because we need ozone to absorb all of that harmful radiation so that we don't get skin cancer, we don't burn up all of our vegetation, the trees and our food crops would burn up without this ozone. So it's very important. But another thing about ozone, because it is so important, it's very important in the stratosphere, but as soon as it comes down into the troposphere, where we are and where we breathe, it becomes an air pollutant. So it flips. So it's very helpful in the stratosphere, but it's very harmful in the troposphere where we are because it's an air pollutant. And so talking about air pollutants, we have the AQI, the Air Quality Index, and it just measures the levels of air pollutants in the air at a certain time. So if it's green, anywhere between 0 and 50, it's a good air quality. And then the higher the value gets, the worse the air quality. So it goes all the way up to 300 or higher, which is kind of like apocalyptic situation. So very, very bad. This is our AQI. For this lab, we did use a website. You are able to look at the AQI of any city or any country in the world. So that's really interesting to see what the different air pollution looks like around the world. If you want, you can play with that website a little bit more. But just make sure you understand this concept and understand why we measure this, why we measure air pollutants, and how ozone is important. So that is it for lab 3. Now we're going into lab 4, Earths and Relationships, and Mr. King is going to talk about that.
All right, team. Let's talk about the Earth and the Sun. So, Earth and the Sun. All right. Well, we know. Let's start off with what we know. So, when we first talked about this in class, we discussed the location of the Earth in relation to the Sun. Okay, so we know that we are 93 million miles away from the Sun. We talked about how we call that an astronomical unit. And the Sun is perhaps one of the greatest drivers of atmospheric processes on our planet. So let's get to talking about that and why. All right, so we know that our orbit is not perfectly circular, right? It is elliptical. It is elliptical. And we have moments where we are many million miles closer to the Sun than we are at other parts of the year. So the point at which we are closest to the Sun is the perihelion, okay? And at that point, we are 91.5 million miles away. I'm sure those of you in my class are happy to see that we actually have miles here. Usually in my class, we speak to Queens, but we are talking miles and such today. So, additionally, the point at which we are farthest from the Sun. So I believe if I step over here, I am farthest outside the camera frame. This is the aphelion. Right? This is the point at which we are farthest from the Sun. So if this side of the frame is the Sun, I am at my perihelion currently, right? But if I travel further away, right, I am at my aphelion, okay? All right. So that's one piece of the puzzle. But let's get into the next pieces. So we know that the Earth tilts back and forth, right? So we constantly wobble, okay, back and forth, and back and forth. If you remember, our maximum axial tilt is 23.5 degrees. 23.5 degrees. This is one of the most important things that you should know heading into the midterm. Is 23.5 degrees is the maximum axial tilt of our planet. So what does that mean? For our planet? Well, what it means is over the course of a year, we wobble back and forth, right? And we can measure certain points that we are at fairly clean numbers. So if you are familiar with the autumnal equinox, right? We're actually doing this backwards. I think the solstice one is here and the equinox is there. We just passed the autumnal equinox. And what that means is equinox equal, let's actually go to that slide. Equinox equal, right? It means that the Earth is receiving equal amounts of sunlight in the circle of illumination. And remember, the circle of illumination is the area of the Earth that's receiving sunlight. But it means that all areas, right, from the North Pole to the South Pole are receiving equal amounts of sunlight. Okay, that's the autumnal equinox. We actually just got done with that maybe about a week ago. But as we continue to tilt, and right now we are starting to tilt away, right? Away from the sun, away from our nearest star. We are going to hit the winter solstice. The winter solstice. Actually, what I'm going to do is we're going to draw some. I'm not sure if you can see the circle, but it doesn't need to be much. So.
Hey, that black marker I was using is really dark.
Okay, I'll use that. So I brought color because I like to distinguish, but
Your students say shout out to the king.
so I appreciate all of you. Thank you for tuning in. So, all right. But when we are tilted at our maximum axial tilt of 23.5 degrees, right? 23.5 degrees. Okay? Certain parts of the Earth receive more sunlight than others. So, in the winter, which we are heading towards, we are about 2 months away about 2.5 months away from the winter solstice, the northern hemisphere will receive less sunlight than the southern hemisphere. Okay? But eventually what will happen, and a lot of my students will remember that I took some of you outside, and I had you stand in areas around a person who we designated as the sun to watch the journey of our planet, right? So once we hit the vernal equinox, let's jump back to the other slide. Once we hit the vernal equinox on March 21st, we will again be oriented at 0 degrees. The Earth, from North Pole to South Pole, will receive equal amounts of sunlight as we continue to turn and tilt and make our way around our nearest star. But then what will happen is in the summer, for us, the days get much longer. And this happens because we tilt towards the sun, right? We tilt towards the sun. So it means that the northern hemisphere receives more sunlight, right? So we tilt towards and get more sunlight. And remember that this dance continues. Year after year, we wobble back and forth as we continue around. Another thing to note is when we are closest to our star, the northern hemisphere is pointed away. And when we are farthest from our star, the northern hemisphere is pointed toward. All right. Before we move on, any questions about solstices or equinoxes? I know I bounced back between the two slides, but I was kind of charting our circular path. So, all right. Any questions? No questions? Okay. All right. So let's talk about the tropics and the circles. So when we look at these, we know they exist, but why do we chart them? Why do we chart them? Well, the tropics are, as is listed here, the lines of latitude that mark the furthest extent of the Earth that sunlight is directly received. So what does that mean? It means that between the latitudes of 23.5 degrees, right? Between the latitudes of 23.5. So let's look at this Earth that we have here. We'll draw the equator, right? Between these lines, we'll do a dashed line here. Between these dashed lines, they always receive direct rays from the sun. They always receive direct rays from the sun. This is the furthest extent of the Earth that sunlight is directly received. Okay? So it means no matter the tilt, no matter our tilt back and forth, as we wobble back and forth on our orbit, they always receive direct sunlight. But there are two other important lines that you need to know. We have the Arctic and the Antarctic circles. Not exactly an inspired name for a circle, but the anti-Arctic. How boring. Okay. And they are at the upper reaches of our globe. And why are they here? Well, these lines mark the extent at which we have points where no sunlight is received at certain times of the year. That our tilt is so extreme at 23.5, right? That certain areas do not receive sunlight at all. So maximum over tilt, and they do not get the sunlight. So in the winter, for us, in the northern hemisphere, as we are tilted away from the sun, the northern hemisphere, the Arctic Circle, will actually have days where there will be no sunrise, and therefore no sunset. Just a long period of darkness mixed with a little bit of twilight. So, all right, those are two very important things to mark. Oh, well, I guess that's the end of that one. I thought we were going right back into solar angle. Okay. All right. Do we have any questions about Lab 4? Any questions about Lab 4? About the tilt of our planet as we walk back and forth? The lines of latitude that you need to know. Okay. So the tropics and the circles. Any questions in the chat?
No, I just think you're cool.
Okay. Well, I'm pretty sure all of the students that have said something in the chat, Tim, Megan, and Jonah, you are all in my Friday class. So enjoy your preview of tomorrow's lecture. You still have to show up, but enjoy your preview. So, all right. So solar angle. Solar angle. What does this mean? Well, when we talk about solar angle, we are talking about the angle of the sun's rays as they strike our planet. And we measure this by something called declination. Declination. And declination is the angle at which the Earth receives light from the sun. Okay? So higher declinations mean more direct light, meaning more daylight. Lower declinations mean less direct light, meaning less daylight. Now, let's think spatially about this. Let's bring this back to this example we have here. You know, just from Lab 4, because Lab 4 and 5, they are like, I don't know, they're two halves of the same whole. Okay? They are close siblings, if not twins. So if you see this, right? If you see this, you know that most likely the tropics are going to have a higher declination than the Arctic Circle because the tropics receive more sunlight, right? And the circles receive less sunlight. Okay? And how do we chart this? Well, we use something called an analemma. An analemma. This is, as we bring this up, I want to mention that the analemma is the single most important part of this lab that you need to be able to use. Again, my students, for tomorrow, we will go over this and we are going to practice this. Yes?
Tim would like to see the raptor comet tomorrow.
Okay, I would like to give credit to Miles for making the raptor comet for me. So, yes, I will bring it back tomorrow. But yes, the declination of the sun is visualized with the analemma. And the analemma displays the path of the sun throughout the year. So if you look at an analemma, if you go to Google and you say, hey, I want to see an analemma, you should tell Google that at this point. And it will bring it up, and it will show you what looks to be the sun moving in a figure-8 pattern, right? But that in itself is a misnomer. The sun does not move, we move around the sun. We move around our nearest star, right? And this analemma charts our movement around the sun as it appears in the sky typically the pictures are taken at noon when the sun is the highest in the sky. All right. But the analemma is important because take note that it shows you three important lines. Three very important lines. At the top and bottom, at 23.5, are the Tropic of Cancer at the top, and the Tropic of Capricorn, and in between is the equator. So you know, and let's take this all the way back to Lab 1, you know that you're being shown a map here. You're being shown a map. The analemma is a map. And instead of it showing you a place on the Earth, it's showing you the path of the sun through our sky. But this can actually tell us a lot, so let's get into what it can tell us. Do not be scared of this. Let me wipe the board here because we're going to write this one out. So take a second, students, look at the math, breathe, and then I'm going to explain. All right. Okay. All right, students, so solar angle. Solar angle. So it is SA for solar angle equals 90 degrees minus, okay, it's about to go crazy here, minus the absolute value. All right, you guys want to see me butcher lambda? Wow, I have butchered lambda. You know, okay, I didn't butcher it this time. That's actually pretty good. You can leave your applause in the chat. All right, so plus or minus delta. Well, that's a hot mess, right? You see this? Can they easily see this?
Yeah,
Perfect.
pretty visible.
You see this, and this is a hot mess. So we're going to work this out together. So solar angle equals 90 minus the absolute value, lambda, equals latitude. So latitude plus or minus delta equals declination. So we're going to. So we've broken this down to be a little bit more digestible. Solar angle equals 90 minus the absolute value of latitude plus or minus declination. I will tell you, 90% of you who are watching right now, I will tell you, all four of you, I think it's my 3 students and me. This plus or minus is where most of you students will struggle. But we're going to take that struggle away. This plus or minus, right here, is the biggest piece, the most important piece of this equation. Because finding a latitude is easy. Most questions I'll give it to you. Most questions I'll give it to you. Here we go. Let's do this one. So, the solar angle for, yes? Nice. The solar angle for Jacksonville, Alabama on November 15th. So, using that equation, how would you solve this? We're going to do it together. So, solar angle equals 90 minus, listen, I'm going to champion that you always set your equation up every time you do this. If you are taking the midterm, you will be coming in to take with me. Show your work so I can at least give you partial credit. This is very important, but always set it up. Always set it up. Your parentheses. I'm going to use different colors and hope they show up because it just helps my brain. So the absolute value.
Green doesn't show up for shit.
It doesn't.
Green does not.
What about the pink?
That's red, but that's pink.
It is pink. Yeah, I know it is because I read it.
Hold on, video's got a little second.
All right. So the latitude for Jacksonville, Alabama, you will be, keep this in mind, write this down, is 34 degrees. 34 degrees north.
I can see the line.
All right. But how do we find the declination? Well, let's go all the way back to the analemma and look at the analemma, right, for November 15th. So you're going to look at that and you're going to also notice that there are months and dates listed on the analemma. So you will go to the bottom of the analemma and you'll see November. And you'll see November 15th falls around 19 degrees south. Because remember, you are technically looking at a map, right? 19 degrees south. If it helps, write the information you know. 34 degrees north, right? For lambda. And delta equals 19 degrees south. So I told you that you would struggle with the plus or minus. And I didn't touch on it right away because I wanted to do it while we were doing one of these. So let's go back. And at the bottom of this slide is the most important clause that you will need to solve this. And these are the rules. You will hear me talk about the rules tomorrow in class for my students. But if the latitude and declination are in the same hemisphere, you subtract. If the latitude and declination are in different hemispheres, you add. So, looking at this equation, I've written down the information we know, right? And I highly suggest you do this when you set your equation up, okay? We know that lambda, right, our latitude is 34 degrees north. But the declination of the sun at November 15th is 19 degrees south. So it tells us they are in different hemispheres. So therefore, due to the rules, you add. So let's do brown. All right. And from here, this is just making sure you do the math properly. So we know that 90 minus the absolute value of 34 plus 19, so 34 plus 19, 53. So, okay. So therefore, 90 minus the absolute value of 53, and I believe it's 37, it should be 37. And your answer to all of these will be in degrees. Let me go back to that. Oh, does it actually do it out for them? It does. How about that? I didn't expect that. Well, there you go. The work is shown to you. I will leave that up there. But we have worked our way through it. Each one of these is a process. You will see step A through D. Be sure that you go through that process. Oh, that's wrong. That's fine. Don't look at that. You didn't see that. You saw nothing. It wasn't there. Okay. All right. That was a lot. And if you have to, when the stream is over, go back, watch as I do this again. But I will ask the chat, would you like me to go through the second one, or do you feel you have a grasp on it? My Friday students, do not worry, we will go through this tomorrow.
Give a moment, there's a little bit of delay.
Yep. I should leave this up here for right now.
So far, no answer.
I'm just going to move on if there's no.
Someone said both. Will we be given the equation?
Will you be given the equation? Typically not. It's one of the few things you have to come in here knowing. So typically not. But don't worry. Don't worry. We're going to go through it tomorrow. And you can always go back and watch this. So nobody said they want me to do the second one. I'm okay if they want to. I'm okay if they don't.
Someone said both, but I don't know what that means.
What?
Your Monday student Jubilee. Jubilee did this all. Oh, yeah, something else popped up.
Let's look at this one. Is this one right? Okay. You know what? We're going to do it. What time is it, Doug?
It is 10:04.
We're almost there. All right. Actually, we'll leave this.
You could just, oh.
You know, think smarter, not harder, students. All right.
Someone said I'd like the second.
Okay. Then we're going to do this one together. So it asks you what the solar angle is on April 25th. So let's write down what we know. Let's write down what we know. So we know that the latitude, or lambda, equals 34 degrees, because that is what we use. 34 north. Write down what you know first. So your declination, right? Your declination, your delta. Well, this is what we have to figure out. So what is the declination of the sun on April 25th? Well, we're going to have to go back to the analemma. So let's go back and look at where the sun is on April 25th. So looking at the analemma on April 25th, we are roughly 11 degrees ish, I believe. A little higher than that. It's like 13. Yeah, it's like 13 degrees. We're just going to go with that. But here's the important part. We see that we are 13 degrees north. All right. So we have the information we know. So now let's go back to the equation. The solar angle, so be sure to write down the equation. So solar angle equals 90 degrees minus the absolute value of lambda plus or minus delta. We continue to set it up from here. 90 minus, and let's input what we have. So 34. We won't fill out the plus or minus, we'll talk about that in a minute. And then the delta, the declination, 13. Okay, close it. So, look at the rules. Let's go back to the rules. What are the rules? If the latitude and declination are in the same hemisphere, you subtract. If there are different hemispheres, you add. As it happens, we are in the same hemisphere. So we're subtracting. We're subtracting. So, from here, it's a math problem. It's a math problem. So, 90 minus the absolute value, 34 minus 13 is 21. Right? And so, 90 minus 21, so 69. Nice. 69 degrees is going to be your answer. If you take the midterm and you show me this, right? What I have done right here, that is full credit right here. If you step through every step of this, and I guarantee you, if you follow the rules, right? The hemisphere rules, right here, and you break this down step by step, you will not go wrong. I mean, as long as you do the math right. All right. So, before we get into the very last thing, how are we feeling about that team? Any questions? Want to make sure I answer any questions about this moving forward, as this is one of the toughest things so far this semester. I'll give it just a second so I can answer.
Give it a full 30 seconds.
Yes. I'm going to go pick up my markers I dropped. We're almost done. All right.
Tim, Megan, and Jonah, I'll say they're good.
Okay. Awesome. You have a perfect head start for tomorrow. Again, Tim, Megan, and Jonah, you still have to come to class tomorrow, but at least you'll have it easier than the rest because you'll have seen this already. So, all right. Let's talk about solar intensity. Solar intensity. So, if you remember, the sun and its direct rays, right, hit our planet. But a lot of the planet doesn't get those direct rays because of the tilt, right? And this is what this solar intensity chart is showing you. But that also means that as the rays hit, their intensity, their radiation is spread out along a larger area because it is not getting a direct ray. Right? So, when we find this number, I left this up here for a reason. When we find this number, right? We find this 69 degrees, we can figure out its solar intensity by finding its solar angle. So you'll see a chart, and you will see the sun angle, the solar angle, right? And you will see that it has numbers in the tens place along the y-axis, right? And the numbers in the ones place along the x-axis. So what you're going to do is you're going to take this number that you find from the solar angle, and you're going to go, okay, it's in the 60s, right? So you're going to go to the y-axis of the chart, along the left of the chart, and you're going to go down to 60. And then you're going to see in the ones place is the 9, so you're going to go along the x-axis, and you're going to find where they intersect. And you are going to see that the solar intensity is 93.4%. 93.4% is what you're going to see here, okay? So all you have to do, the solar intensity gives you an extra step. Find the solar angle, go to the solar intensity chart and go to the tens place. The tens place will be your first number, right here, right? And that is your x-axis, okay? And your solar intensity is your, you find the y-axis, or the x-axis, and find where they intersect. And that is your solar intensity. All right. And that, students, is all I have for you. Good luck on your midterm. If you have questions, feel free to ask. To my students, I will see you tomorrow. This will be a lot easier for you. Thank you for tuning in. If you have any questions, feel free to email us. But if not, we will see you in class next week for your midterm, and good luck. And that will be the end of.
No questions.
Awesome. How crazy were my